Hassan Azad, and first I'll go into his bio. Hassan Azad is an assistant professor at the U.S. School of Architecture. He's a scholar known for his research, teaching, and practice in the areas of architectural science, building technology, and particularly architectural and environmental acoustics. Dr. Azad is director of the Environmental and Architectural Acoustic Research Lab, EAR, where with his team, he conducts research projects that encompass a variety of topics. These include technology integration with architectural design, computer programming, and simulation for architectural and acoustical applications, and smart connected built environment. At the School of Architecture, Professor Azad teaches several undergraduate and graduate courses. He is also a member of UF's doctoral research faculty and supervises doctoral and master's-seeking students. He teaches environmental technology 1 and 2 and graduate seminars on topics of architectural and environmental acoustics. And this is the abstract of his topic today. Environmental noise is a critical pollutant defined as the unwanted or harmful outdoor sound created by human activities. It is directly associated with health and work-related problems such as hearing loss, children's cognition problems, cardiovascular problems, and other personal, psychological, and physiological damage, as well as reduced work productivity. Noise is especially critical in urban environments due to the plethora and variation of noise sources, ranging from ground transportation and aviation operation to different sectors of industry, including construction. The primary goal of this research is to use machine learning algorithms to replace physics-based solutions to the problem of environmental noise modeling with its AI-generated counterpart. The objectives are to significantly reduce the time that is required to obtain physics solutions and to produce a user-friendly method to this problem compared to running numerically supported simulations. And I'll give the meeting over to Dr. Azad.
Thank you very much. So I'm gonna start by sharing my screen. I'm guessing everybody sees the screen, right? So as it was mentioned in the introduction, I'm working on this project with Dr. Ian Flood and 2 other of my students, Priyam Selgar and Ridesh Chowdhury. We are working on the application of machine learning in the prediction and modeling of the environmental noise. I want to start by saying that the project has expanded. So at the moment, actually, the application of machine learning is not only limited to the prediction, and we are also working with the different measurement techniques, which actually the primary purpose of this presentation is those data collection techniques that we are using at the moment, in addition to the simulation, numerical simulations, basically. The goal of the research, again, is exploring the tools of machine learning to predict environmental noise metrics in order to develop an optimized noise monitoring solution. So why we are basically interested in this? First of all, as again, it was mentioned in the abstract, we all know that there are a lot of harmful effects of noise on human health, different health-related problems. I just read this, the WHO report, which is almost current, 2011. 1 million healthy life years are lost every year from traffic-related noise, only traffic in Western Europe country. And then it's a serious problem. And then and another reason that we think that the study of noise, being able to monitor noise in real time, being able to predict noise in real time, it's the use of this information, this data for design, the future design of urban infrastructures. So I can give you this, actually in the next slide after this, I will give you one example of what would be the output of this research. So basically what I want for you guys to be aware is, at the beginning of this presentation, I like to get you this information that, so what we are doing all of this, what would be the outcome at the end, basically. So let's talk about the existing solutions and their problems, and then what are our objectives, and then talk about the one of the possible outcomes of this research. The existing solution, if we try to, categorize the solutions into two categories of solutions that are related to the measurements of the noise and solutions that are related to the simulation. In regards to the measurement techniques that we use today, first of all, the devices are usually very expensive. They come in different kits, different packages like this. For example, this is only one sensor. This part is a class 1 microphone. I don't get to the details of the difference between different type of microphones, but what we use is the high end because of the recommendation of different standards, European ISO standards and ASTM standards. All of them recommends class 1 microphones. So, and then there are analyzers, usually with the help of cables, long cables. They are connected, and then there's environmental issues to be taken care of. So the whole units that you see here is almost around $10,000. And you imagine, for example, for a location like this, which is actually the location that we are working with, it's it's our campus, right? I will explain this shortly. So just assume that even for a small area, for example, like this, you might need like 10 sensors, easily 100 grand, which is expensive. And then, of course, we at the moment there are remote solutions, and actually the solutions that we are kind of providing with this research is also a remote solution. But again, there are still, even in remote solution, you just are getting rid of this cable, but it's still the analyzer. It's in a separate location. Sensor is in another location, and the scalability issue is just is something that I've actually written down here. Operational and scalability issues is still a thing working with this professional noise monitoring technologies today. When it's come to the computer simulation, the problem there, that we are facing at the moment is basically we have two different methods. One method is an estimation method, computer program, commercial programs. Actually, we are using one of them at the moment. They're not that accurate because they're using estimation method. But then if you want to use computational, if you have computational resources, and if you want to use numerical methods, which are kind of the most precise method to simulate noise and any sound related environment, then you need to use a lot of computers. That's actually one thing that we are at the moment trying to develop and see for how much of the space we need, how much of the computational resources in general. But these are problems. We think that in either of these two categories, measurements or simulation, maybe there is a chance that use machine learning, and then try to come up with simulation for, let's say, a new design, urban design for a community, and then try to predict the outcomes of that new design. By design, I basically mean design of infrastructure, roads, highways, and then see what's the outcome. This is regarding the simulation, and also for the measurements. Although we are developing at the moment for the purpose of our research, we need data. We are developing a smart noise monitoring solution, but then we think that maybe even if this development is like a lot cheaper, for example, or kind of addresses the issues here, still maybe machine learning can also optimize that monitoring solution, basically going one layer down and try to get even better with the monitoring. So these are basically our objectives, mostly optimization regarding computer simulation of noise, and also the measurements of the noise. So it's just a very simple map here, it's Orlando. I think that regarding, again, the simulation and measurements, what the outcome of this research might be is that, for example, if you can take a look at this red dots, if that's the case, that we need to have a, let's say, remote monitoring system, maybe we only, for the major locations of the noise source, we can have our developed remote monitoring system, and then for the rest of the infrastructure that create noise, traffic noise, for example, mostly, we can have our machine learning solution to predict the noise for us, and maybe there's no need for having sensors all around the city for their traffic noise or different sources, other sources of noise. So that's basically, that could be one of the outcome of this research, basically like a platform in which there are tools you can use to predict the outcome of noise by interventions of design of infrastructures regarding highways and roads. And at the same time, maybe you can kind of optimize the number of sensors, noise sensors, reduce the number of sensors, and then maybe at the end even get rid of the sensors, and then just have machine learning to measure the current noise, basically, without sensing that. The workflow that we are trying to follow is that basically what happens in our research, at least at the moment, is because we don't have available data to use, we need to collect the data ourselves. And you can imagine that if you want to have a large data set to work with different machine learning algorithms, you need to spend a good amount of time, or you need to put effort to collect this data if you don't have that data available for you. So that's the case for us. We didn't have data available, at least in the state of Florida. There are some kind of, I'm getting off topic, but there are some data available, but it's not at least in the location that we are interested in. So that's one of the reasons that we try to develop our own monitoring system, because we started to do the measurements and we realized that how expensive and how inefficient is the current method. So we just added one more big task actually to our research. So fortunately, the development of the monitoring system is finished. Actually, one of them is going to be installed in the location, and I will show later in this slide with the help of UF utilities. So we will be basically fine within a month from now to install create our own sensors and install all of them on the locations that are needed. And then the next step would be another way of data creation of data or production of the data with the help of simulation, numerical simulation. Let's say that we have all of this, then there's a time to be able to see what are the machine learning algorithm, or what's the measure that we can take to include machine learning here. Basically, what we are doing is we like to get use of cameras recording on the traffic signals, and then having the different image processing system to be able to count the number, type, and speed of cars, and then kind of synchronize that information with the measured and simulation data in real time for that the specific time or moments of recording, and then try to predict or to find a correlation between the measured and simulated data of noise for that again a specific instance of time, and its image processing of the traffic noise of the number of the vehicles and the speed of the vehicles, and also the type of vehicles. These are basically the input of the simulation models as well. So when you want to do the computer simulation, you need to know about the basically the flow of traffic, the type of cars, number of them, and then of course architectural features of the environment are this like another features as an input. I'm not sure if we can get to this into this level of detail to incorporate environment as well. But that's the final goal. This is a continuing effort, research, and then eventually we want to include every possible input in our event simulation model and also machine learning model to be able to predict as accurate as we can the level of the noise. And then of course there are data verifications that we kind of compare the result of machine learning models with the result of calibrated simulators and measured data. The project timeline that we are following, excuse me, this is actually a funded project by UF, the AI Catalyst Fund, right? So we are finished with the phase 0, which was finding different sensors, deciding between different classes of sensors, microcontrollers, and then what we are doing at the moment is we are deploying the sensors. We are working with computing the acoustical parameters that comes out of the sensor. So because we are doing like every data collection step ourselves, so we are also creating the analyzer ourselves. So we sense the data, we analyze the data, we pre-process the data on the sensor itself, and we are creating something very compact for doing all of this. And then we are remotely sending the data to UF network at the moment. So, and then we are also doing the simulation and exploring different machine learning algorithm. This is what we are trying to finish by the end of this month, and then try to deploy and train the machine learning models. And of course, that's the simulation and the measurements. As soon as we have all the sensors installed, it's going to continue until the end of the project duration, meaning that continuously we get more data, and then we kind of recalibrate our models, basically. Talking about phase 1 and sensor creation, we went through different kind of manufacturers that create microphones. There are different type. I don't want to get into details, but at least you can know that the class 1 microphones, they come with different connections. Like this one's XLR connections, or this one we call BNC connection. Each of these two methods, you need different power source to include in your package for the microphone. So microphone and preamplifier, they both need power supply. So this one is the one that comes with XLR connection. This one is the we call signal conditioner that is used for powering the other type, the BNC type. And then we are using Raspberry Pi for pre-processing and sending the data. We are using this cellular data hat. We are using AT&T carrier to be able to transmit the data wirelessly to UF sensors. I'm sorry, to UF networks, and also there is GPS model that help us to locate the sensors. So eventually, we want to have a platform that shows the location of our in real time, basically presents the measurement data and then the location of each sensor. So this is the time that we were working with different part, and we were trying different microphones and trying to see different stability versions of using different microphones and different processors. And then, of course, the package itself. Eventually, we came up with this list of items, and then the recording times, how we are going to do that. What we are doing at the moment is that there are packets of data being uploaded every 15 minutes. It's around 80 megabytes, each of these packets. These are 15 minutes of recording. We intend to do this recording 24/7 when it starts and when everything is calibrated and then works perfectly well. So it's going to be around 7.7 gigabyte of recording per day per sensor. And at the moment, we are working in the location that requires of us to create 6 sensors. So you can imagine how much data we need to do to record every day and send to our network to basically process. We have created a Python code again for, because it's not only the recording, you have the recording and then you need to compute some parameters. So we don't record and basically listen to the recording. Of course, that actually one other thing, when you do project, you realize that there are opportunities to develop and you come up with new ideas, right? So actually this recording, we are thinking that later on we can actually do something with the recorded audio, basically use audio as an input to generate noise monitoring solutions and basically noise data. But that's something in the future. But we are actually, again, analyzing the recording to be able to compute different acoustical parameters. Again, the commercial solution, more than 8,000, usually around 10,000, we come up with the same kind of use of class 1 microphones, and we created a setup that is less than 2,000, it's 1,900. This is the final, not exactly the final. We actually realized that we need to do something at the bottom because of the environmental issues, birds and everything. But at the end, there's going to be a box like this. The dimension of the box would be around 4 inches in height, 6 in width, and 10 inches in length. There's going to be one part here that the sensors sticks out of this side, and then at the bottom we have a power plug and we have an antenna for the remote kind of transmission of the data. So this is going to be our units. Again, I thought that this is final, and then when we talked about how to install this with UF utilities, we realized that we need to also take care of some other issues as well. But hopefully we will finish that by I believe 2 weeks from now. And then the good point is that we will be kind of working with utilities, and then we get good kind of consultation from them in regards to environmental issues like heat and then rain, and also the birds basically. And then but what we have done so far is actually the device is working well. It's been like we have done different robustness experiments running this for like 3 days, 4 days continuously, and measuring the data and sending that. Actually, we did it on my office and the facade of the architecture building. So we did actually some noise monitoring around the building, architecture building basically. So for the robustness, what we are interested in is that all the scripts are automated to run on restart. So if there is a kind of sudden power kind of block or any sudden interruption in data transmission, the device itself runs and restart the measurements restarts, and also the data transmission. We have remote access, both SSH and VNC, to each unit, and then the data we actually have name and date. So that's something else that we try to do to kind of increase the robustness of the monitoring solution. I talked about the specification of the data, the minutes of the packets, and it takes about 3 minutes right now to upload one packet, and which is not that bad. But if we want to have a better, maybe we can use another carrier, or this is the highest level of the unlimited data that we could get from AT&T. So if that was a problem, we can actually, of course, we can go with another provider. Power source, only one power plug is needed, and on each traffic signal, each pole, basically there are kind of control boxes that allows us to use one basically source of power. 110 volt is more than enough for the whole sensor. We have power adapters inside the sensors. And I talked about the scalability issue, precaution measures. What is it? We thought maybe there are cases that there the internet goes off for any whatever reason, and we're not able to remotely, for example, from a very remote connection, access the microcontroller, we have created an SSH hotspot on the kit itself. So the only thing that we need to do is go to, we don't need to go up to the pole, but we need to get close to the pole. And then we can take care of the basically the data transmission problem. So if I want to be more specific about what we are going to do is we are thinking about these 6 locations. And by the way, I didn't kind of explain what is these like green dots here. This is a project being carried out by UF Transportation Institute. And the project is basically, these are what they call roadside units. And there are different sensors installed. The sensors are mostly cameras and also LiDAR detectors, LiDAR sensors. And I believe they have some radar sensors as well. So these are the sensors that are already implemented with a different project, Florida Department of Transportation, and then City of Gainesville, and different cities in actually the state of Florida, they have implemented this project. The reason that we are interested in this and the locations is basically, we think that we can add one sensor basically to the already installed sensor in these units. So we think that there is a potential to collaborate with Florida Department of Transportation and propose to them that, hey, you have these video sensors, camera sensors, and LiDAR and radar. Aren't you interested to add one more sensor to your roadside units packet? So actually there's a certificate process. We're trying to go through the certificate process, but at the moment we can actually place our sensor next to the sensors. So that's what we are doing at the moment. So we are placing our sensors in these locations. And the reason that I'm interested in this location, there are other locations in Gainesville that we have these roadside units. I think Archer is one of the kind of prominent noise sources. But this location, we have Shands Hospital, and we have Malcolm Hospital. So there are sensitive communities when it comes to environmental noise. One of them is hospitals and healthcare communities. And then, of course, there are schools, for example. That's actually the second target on my list. As soon as we are finished with this, if for future projects, we try to see if we can find kind of noisy roads or places that there are a lot of environmental noise sources, and also then next to them schools, for example, or any other type of maybe, for example, nursing homes. So we start basically with sensitive communities. I'm actually really glad that I found this UF Transportation Institute project. It's actually called iStreet. So if you can search for this UFTI iStreet, you can find it quickly. We were able to work with UFTI. We were able to work with City of Gainesville, GRU, utility. We are still continuing to work with these institutes and departments, and also in our University College of Engineering CISE department. Dr. Ranko is actually doing some sort of same project using these roadside units, this kind of cameras and image processing. They're actually doing, they have started before us, to be honest with you, and then they have run their different machine learning models. But as the input, they are actually doing same. They need the number and type of the vehicles, and they're doing some I believe the research is about traffic accidents, if I'm not wrong. So anyway, I'm really glad that we were able to collaborate with this number of institutes and people in our university. Uh, so regarding the the calculation of the acoustical parameters out of those recordings, I don't get again into different levels of details, but it's suffice to say that there are sound levels, like equivalent continuous sound level. There are equations. You just use the equations, and then you can basically the equations that needs some measures of frequency weighting and time weighting, and that's not a kind of complex issue. So there are different weighting filters. Basically, you use those filters, you get different weightings, and then that's the standard. The standard needs you to compute these levels when you monitor or when you predict noise in environmental settings, basically. And then we are trying to actually, we have done this, actually not trying. We have finished this computation. So our codes basically calculates all of these. This is the one of the kind of screenshot of the packets that are being uploaded again at the moment on UF networks. I keep saying UF sensors, excuse me. And then one of the output of those. This is the basic output that we get from the recording, and using this, it's basically sound pressure in Pascal. So basic physics, sound pressures in Pascal over time. This is the basic information that we get out of the recording, and then we compute the parameters, and we do the frequency and time weighting that I showed previously using this simple graph. Some of the recordings that this is one packet, almost 15 minutes in time. We have C weighting here, frequency weighting, A frequency weighting, and we have LAEQ stands for sound pressure level, A weighted equivalent time. We did pick as well different kind of presentation of the data. We actually need to show these when you do the real-time measurements. It's better to have different, maybe for example, at the end, the platform shows different graphs. In real time, you see different numbers for different frequency and time weighting. For time weighting, I decided to go with 1 minute of interval. So every 1 minute, you have a kind of the recording is getting updated, the presentation of the data is getting updated, and then in every 1 minute you have fast, slow, and impulse time weighting presentation of the data. This is for one of the packet that I showed in the previous slide. This is for the first minute, and this is for the last minute. Simulation, to be honest with you, we weren't able to do much at the moment. This is the computer commercial program called SoundPlan that we are using. But again, the commercial programs, they use estimation method. They don't do real calculation of the noise using numerical techniques. But we are working with it's actually use a spectral element method if you are familiar with different numerical methods. So we are working with a solver that uses spectral element methods to compute noise or simulate basically noise. And then regarding the machine learning algorithm that we think that we will be using, mostly I think we are exploring, to be honest with you, at the moment. But the result of our discoveries shows that region-based convolutional neural network and YOLO, these are the kind of tools, available tools that we better to get use of for kind of being able to create a machine learning algorithm that help us with the prediction of the number, type, and speed of the vehicles using the camera's feed. A less kind of less advanced method, but quicker but less accurate method would be using loop detectors instead of cameras. Loop detectors just give you the number of it gives you the flow of traffic, but you don't have the information about the type of the cars. Maybe we start with this, and then we go with a more sophisticated method. But as input, again, we need number and speed and type of the vehicles, maybe number of lanes per road. And at the end, we tend to include also architectural features, buildings, even the materials of the building, their reflection coefficient, for example, trees. I mean, there are, to be honest with you, there are a lot of number or features that we can number of inputs and features that we can use, but we are at the beginning again at this stage of this. So we try to do all of this, but maybe in a couple of months or maybe in the next DCP seminar series, maybe I have more to present regarding this part of the research. And this is two of the locations. I showed you those 6 sensors, right? So this is the actually one good thing that we have done in collaboration with City of Gainesville. Now we have our computers and they're at their location, and we have remote access to this cameras. So we are actually recording. So we're not that kind of at the beginning of the working with machine learning part of this project, but we have currently access to the cameras of those 6 locations, and we are recording cameras. We are recording cameras feed basically for those locations. And this is one of them, and the right and the left is Archer Road and Newell Drive, and the other one is Archer Road and Gale Lemon Drive. And for the next phases, what we are thinking to do is basically installing again all this. It should be 6 sensors. Sorry about this. And we want to continue work with City of Gainesville, Dr. Ranka's lab on getting helping us basically. One of the objective of this UF Catalyst Fund was for people who are at the beginning of their interest and their kind of journey into machine learning to be able to get help from people who have been working in this area for quite some time. So that's actually one thing that I need in this area, to work with people who are expert, and then they can help me and my team with the machine learning part of this project, basically. So we continue our collaboration with Professor Ranka. We continue again the simulation and measurement as soon as we start the measurements on all of the 6 sensors. We continue to do that for the whole duration of the project. And deploying of and training the machine learning, and these are the phase 2, calibrating the models. And finally, the phase 3, as I showed at the beginning, the last 2 months, we try to conclude and the project, report the result in Explosive Future. If we have time for, again, including architectural building elements by that time, we definitely try to do some work in this regard in our phase 3 of the project. And yeah, I think that's the end of the presentation. Thank you, everybody. Thanks. Do you want me to keep sharing the screen, or?
You can do whatever you'd like, Dr. Azad. I have a question. Do you mind if I ask it?
Yeah, go ahead.
It sounds like Dr. Remka is doing the crosswalk study with UFTI and Wardheim Civil Engineering. Does that sound familiar to you?
I think, yeah, that's the project. Yeah.
Okay. Just wanted to see if that was the one. Thank you.
Yeah, exactly. Yeah. Sorry, there have been a lot, not a lot, but several projects that we've been kind of thinking about to have collaboration with. We basically submitted a grant proposal. I'm the PI, Professor Ranka, co-PI, and another faculty member, co-PI, one faculty member from another university. But yeah, you're right. That was the project.
Because it just occurred to me that because he's doing that work and he's interfacing with smartphones and some kind of sensors within cars, that might help you out in some way.
I think so. Um, there are a lot of opportunities. For example, I know that there are sensors also in the buses in front of them. I think um, maybe that those sensors can help us with the speed detection of the the vehicles and also the buses itself. Um, are I'm thinking right now that's out of my head that you talked about the sensors in cars
They were trying to work that out the last I checked in with the studies. There's several studies, but the crosswalk is basically to make crosswalks more secure and safe for
right.
students and pedestrians. And the idea is to have some kind of sensor, maybe attached to smartphones or some kind of interface with the vehicle electronics. And I don't know how far Dr. Ramka's gotten with that, but it seems like because you were dealing with ideas of type of car, speed, that you'd be able, I don't know if there would be issues with privacy, but if there weren't, that you would be able to identify the cars and the speed.
Right, yeah, exactly. I'm assuming that they are going to be really concerned about the speed, and their concerns is different from mine. I use the speed. I don't care in this project about speed being high or low. I just want to get because there's a relationship between the speed of cars and the noise that they create. So I'm interested only in the number, but I can get the number from them. Thank you for letting me know. I mean, I definitely can imagine that they are interested in the speed of the vehicles.
Thank you, Dr. Azad. I'll mute myself again.
Thank you. And I'm happy to answer any question if there are, and if I can.
I have a question.
Yep.
So when you ran the code, did you go back and forth between running the code and verifying the data you have? Or it was totally clean and you didn't have this issue?
Can you elaborate more? Which data that I have?
Like, so you said that you did a data verification between the data you collected and the simulation.
Oh, no, I haven't done it yet. Yeah. So that's actually on my list. I haven't compared yet. That's in my list, of course. Yeah. I haven't compared any simulated data with the measurement, but I'm relying on the measurements as the reference, and then my intention is to calibrate my simulator with the measurement data, but I haven't done yet.
Okay.
Yeah.
Okay, then good luck.
Thank you. Let me stop the sharing.
I'll unmute myself again. So we still have 15 minutes. So it's up to you, Dr. Azad, whether you want to give time to people to formulate their questions.
I mean, whatever you suggest, I'm okay with that. I think I'm thinking if I have more recent exploration of the sensors, or how we are working with creating this box to maybe present something more, but yeah. Let me check. So I can actually, if you are interested, I can actually talk about the issues that we are trying to take care of regarding the like heat and also birds problems with the sensors.
I did have a question about the birds. It's kind of a, what exactly will they be just messing with it, or is it just their actual mess that they'll leave there and it'll interfere with transmission?
So actually, let me. I wish I had a kind of. There are bird spikes that you need to put. So what is missing in this picture? Let's put it in this way. I need to include a windshield here. Windshield help with uh, reducing the noise created by wind. So maybe we're not interested by, maybe the noise from winds interferes with the recording of noise from the real source of noise, which is traffic. So what is missing at the moment here, as you can see here, that there's a windshield, and after the windshield, like in front of the windshield, there should be a bird spike. They just tend to mess with the windshield, and then as soon as there's no windshield, and then they go and try to mess up with the microphone. And these microphones are very sensitive in their tips, so it's better to for these, like the tips of the microphones being very kind of protected. And that's something that we need to take care of. There are commercial products that like protectors for noise sensors, environmental noise sensors, but again, those are really expensive. I'm not sure why, but like a piece of like plastic, it's for I've get quotes from different companies, no less than $500, but some of them like $650, $700. I'm not sure if it's a good thing that I'm kind of very kind of interested in creating something that eventually it's very cheap, that can be used in like a very large number. But that's something that I'm intended to do. Maybe there is a product that at the end is like $1,000 per $1,000 per box, and then you can install that in the different location of the city, and then, or even let's say there are constructions, you have 1 year or 2 years of constructions, for example, in a large or even relatively small, for example, site, and then you are asked maybe by neighbors, or there is a like code that you need to follow and present the noise that you are creating, noise data that you are creating that environment in like continuously in real time, to show that you are not exceeding the standards noise level in that site. So maybe this coming up with a very cost-effective solution is not such a bad idea here. The other issue is that in Gainesville, for example, right now I'm thinking of a concept of box within a box, because of the heat issue in Gainesville, and I'm actually looking for different fans and also cold plates that I can use in the internal box to be able to kind of work something out with the kind of a heat issue here. And also, of course, rain, we need to be able to come up. This box is a IP67 rated box. There are different ratings. 67 is actually a very good rating in respect to rain. But then when you kind of have some part of this, like power plugs getting out of this box, then you are kind of damaging that rating. Then you need to also use devices. For example, this cable glands, this is also IP67 rated. So these are the issues that we are trying to work with at the moment. Having everything in the box, with the box basically, regarding the exterior of the box, IP67 rated.
Have you gotten suggestions from UFTI or civil engineering about their transmission boxes and solutions they've created?
I've been in contact with them. It's the kind of general back and forth. UFTI said that the implementation is done by City of Gainesville, not us. We just have this access to the data and recording. City of Gainesville says that Florida Department of Transportation, and then actually University of, what is that university in Tallahassee? University of
Florida State?
Florida State University, yes. So apparently there was a research lab that this whole project started from there in collaboration with Florida Transportation Department of Transportation, and that's the end of the this communication exchanges of emails that I kind of was able to work with, and then come up with what is at the kind of the last chain of this research project. I haven't been able to contact them yet. But yeah, actually, that's a very good idea. I try to find the end of the chain, but I think I have found it, but I haven't contacted them yet.
Because it seems like the mechanism for civil engineering wasn't affiliated with any other, because I think you're talking about the sustainability people over at FSU. And they did also get grants for some things having to do with that whole plethora of UFTI studies. But in terms of Dr. Ronke's, I think that they're just getting the mechanism themselves. I'm not sure about that. I just wanted to offer it.
Sure, of course. Thanks. Well, of course, it seems you know a lot of people. I should have contacted you. I mean, you didn't know my project, but
yeah, Dr. Azad, if you want to discuss it with me,
sure.
Anytime. You've got my email.
Yes,
I've done too much talking though. I'll give somebody else a chance.
Thank you for offering the hope.
It appears we have crickets, so we have no sound here. So if it's all right with you, Dr. Azad, we can just go ahead and end it. I've really got a lot out of this. Thank you.